So, since the retinal images are the same, but we're perceiving one as a close corner and one as a far corner, it must be that the lines must be different sizes. Right? Remember the thing with the angle, visual angle. Now the problem with this though is, well, maybe that's not exactly what's going on, because you can do this Mueller lie illusion with circles on the lines instead of lines, and you get the same perception. Even though there's no corners, you get the same perception, and you also get it for 3D display. So here's the dumbbell version, right? So here's this line and this line, and we have the balls at the very tips of the line and the balls sort of going through the lines, right? Those are the same lines. They're the same distance, and yet we perceive this one as being longer than this one. So the whole corner thing probably is not a very good explanation. And here's another example. This is a three-dimensional Mueller-Lyer illusion where we actually have two outside corners, right? And we have, two inside corners and two outside corners. And notice that the distance between the distance x and the distance y is identical, but yet it looks like these two guys are closer together than these two guys here. It looks like A and B are closer together than B or C. So given all of this, what's another explanation? Well, one of the explanations for the Mueller-Lyer illusion is the conflicting cues theory, that our perception of line length depends on the actual lengths of the vertical lines and the overall length of the figure. So we are actually looking at the lengths of the lines, but we're also taking into account the entire size of the object or figure that we're looking at. So we take all of that into account and we compute, okay, it looks the same, but the whole thing makes it look like it's different. So the conflicting cues get resolved somehow by making us perceive that one line or one distance is greater than the other, when in fact they're not. Here's another one right here. Again, the distances between the points in A and B are identical, but it looks like the points in A are closer together than the points in B. And in this new conflicting theories explanation, it might be that, yeah, we are looking at the distance between the points, but we're also taking the entire object into account. So we have these two conflicting cues. We have the distance between the points, which is the line, but we also have the fact that this object sticks out far outside of goes over the lines, and this one stays inside the line. This one looks like it's smaller. So the objects are in fact smaller. This object is in fact smaller than this object. So we're probably weighting our perception, I should say, with that fact, weighting our perception of distance with that fact. So the perception of distance is going to be altered by the fact that this object is bigger than this object, and therefore we're going to perceive this line as longer than that line, even though they're the same. Another illusion is the Ponzo illusion. And this is where horizontal rectangular objects are placed over railroad tracks in a picture. And the far rectangles look like they're larger, but in fact they're the same size. And so, here we have an example, right? So we have these tracks going, which is giving us this perception of distance, and then we superimpose this picture of I don't know what this is, like I have no idea what that animal is. It's some sort of mammal, right? But if we put the mammal here and we put the mammal here, all of a sudden it looks like, oh my God, this thing is tiny and this thing is huge. Not only that, but it looks like the absolute size of this guy is smaller than the absolute size of this guy, when in fact they're both exactly the same size. Again, we have these conflicting cues, these misapplied cues. So we're using the cues of distance to inappropriately judge how far away or how big something is. The Ames Room is a very famous example of size constancy. Basically, what you have is this room that looks normal when you look at it straight on. But what happens is the room is constructed so that it's crooked. So the ceiling and floor on this side are much closer together than the ceiling and floor over here. But the windows and the floor are painted so that you can't really tell that they're crooked like that. So when somebody walks from here to here, they magically shrink. And when somebody walks from here to here, they magically grow. And the reason for that illusion is because our brain, our perceptual apparatus, is assuming that this room is a standard, regular room where the walls and the ceiling and the floor are all normal sized, when in fact they're not. I do have a video that I will post of this so you can see an example of the Ames Room. So here's the way the Ames Room looks, right? So this is a little creepy, right? This dude looking at these two chicks through a peephole, but whatever, right? So in this Ames Room, the way it works is the room is crooked so that this part of the room is much longer than this part of the room. But the windows and the floor are painted so that you can't really tell that. Also, the floor is crooked so that the floor here is lower than the floor here. So when somebody walks over there, they're walking to a higher floor and to a area where the floor and the ceiling are closer together. But since the windows and floor are painted in such a way that you can't tell, that it makes the room look like it's normal size throughout. You get this illusion that, well, the room is normal size, so my brain has to make the people appear like they're growing and shrinking. And I will post this video so that you can see it. So one of the explanations for the Ames Room illusion is the size distance scaling. So the observer's brain thinks that the room is normal, and therefore the women are standing away from you at the exact same distance. The woman on the left has a smaller visual angle. So, remember that formula that we had, right? She has a smaller visual angle, so she is actually appearing smaller on your retina. But since the distance is identical, her perceived size is smaller. Relative size is another example. We're looking at a woman who is almost the same height going from floor to ceiling versus another woman who can't even reach up and touch the ceiling because of the way the floor is crooked. So we may also be using relative size to compare the size of one woman to the other woman. This is an illusion that hopefully you've seen at least once in your life because it's beautiful. The moon. Sometimes when the moon is right on the horizon, if you've ever seen the moon on the horizon, and this actually happened fairly recently, I remember, but it looks huge, and then when it goes up, it seems to shrink. Why is that? Well, one of the possible explanations for that is the apparent distance theory. When the moon is next to the horizon, it's next to distance cues. It's the horizon itself, any buildings that are on the horizon, buildings that are, and trees and objects that are, going toward the horizon. So when the moon is close to the horizon, The distance cues that are present may give the impression or the illusion that the moon is actually bigger than it is, that it's closer to us than it is. We perceive the horizon as being further away than the sky. So when the when so in other words, we have a perception of distance of the horizon, but we don't really have a perception of distance with the heavens. We know how far, we have a sense of how far away the horizon is, but we really don't have any sense for distance when we're looking at the sky. This has been referred to as the flattened heavens, right? We just don't know. We have no clue we have no scale of distance when we're looking up in the sky. So since we have a scale of distance when it's closer to the horizon, and then the moon goes up and then it appears in the sky, we really don't know how far away that moon is, and we can't judge its relative size relative to anything else. The moon has the same visual angle in both cases. The moon doesn't actually go further or back or shrink. It has the same visual angle, so it has to appear larger at the horizon. Another explanation is the angular size contrast theory. The moon appears smaller when it's surrounded by larger objects. So if the moon is surrounded by objects, so if when the moon is up in the sky, it's surrounded by just the blackness of the sky. So maybe that makes it look smaller than it does when it's further down and closer to things that we know about. We're not sure exactly why this illusion happens, but it's a powerful illusion. I mean, the moon really does look ginormous when it's close to the horizon, and then it shrinks when it's in the sky, and we really don't have an explanation yet as to why our brains are doing that. And here's a great picture of it. I mean, the two moons on this picture are identical in size. But in fact, the one on the bottom looks bigger than the one on the top. We have the same visual angle because the moon has not changed its distance or its size. But the moon on the horizon just looks bigger than the moon that is elevated, simply because we have no frame of reference up here. Different critters, of course, use different senses for perceiving depth. One of the differences that you can see among mammals is critters that have eyes in the front versus critters that have eyes on the side of their heads. And which will typically, a general rule of thumb is that critters that hunt other critters have their eyes in front, and the critters that get eaten by other critters have the eyes on the sides of their heads. So, for example, cats. Cats are predators, they're carnivores, and so they have their eyes in the front. And the reason they need eyes in the front is for binocular disparity. They need to be able to judge very accurately the distance between them and their prey. But if you're like a squirrel or a bunny rabbit, you have the eyes on the side of your head because you're going to get eaten by those other critters. And so what you're going to do is you're going to use those lateral eyes on the sides of your head to have a wider view of the environment so that you can look out for critters that are trying to eat you. Now, this is going to come at a cost. Animals that have eyes on the side of their head don't have as good depth perception, but they don't need it, right? I mean, as long as they can avoid getting captured by a predator, they'll be okay. So here's a kitty with the eyes in the front, and a bunny with the eyes on the side of its head. Locusts use motion parallax to judge distance. So as they're flying through space, they use the relative movements of things to judge how far away things are. So things that are moving rapidly past them are close, and things that are moving not too rapidly past them are far away. Bats use echolocation to judge distance. So bats actually They can see, but bats aren't blind. That's just a myth. But bats actually emit ultrasonic sounds, and then those sounds bounce off of surfaces, including bugs, and bounce back. And they have very sophisticated mechanisms in their brains that allow them to note the direction from which sounds come from, as long as how long it takes that sound to come back to their ears, and they use that to judge distances. As in this example here, this bat can emit ultrasonic sounds. So it emits ultrasonic sounds, and the sounds bounce off of things like buildings and trees, and of course prey, like a moth. So we've studied depth perception in infants and babies, and we know that binocular disparity starts becoming pretty important to them fairly early in their lives. Now, one important thing you need to know about binocular disparity is, of course, obviously binocular disparity is dependent upon our ability to move our eyes together in unison and focus on something. That's called binocular fixation. In other words, you have to be able to do that. You have to be able to move your eyes in unison and focus on things and fixate on things. Very young babies, like 1 or 2 months, can't do that very well. They really can't do that until they're about 3 or 4 months old, and that's when depth perception starts becoming more and more important to them. Then later on, they start developing the ability to perceive depth in picture cues. And then, of course, as they grow and develop, they start to learn to develop depth from sizes of things, and also depth from shadows. Babies later on in development, you can use shadows to tell how far things are. So here we have an example of an experiment where the baby has special glasses that will enable it to see 3D, and we have this illusion of a square floating in front of a box. And if the baby is able to see in 3D, what they've done is they've changed the picture so that it looks like the square is moving. And if they can see in 3D, they will follow the square. They will actually follow it moving back and forth. If they can't see in 3D, then it's going to be flat, and nothing's going to really be moving for them. So in this way, we can tell at what point three-dimensional processing becomes apparent in very young infants, and usually happens around 4 or 5 months of age, thereabouts.